Hello. In this and the following two presentations, we'll be taking a look at the most important interactions of ultrasound with soft tissues. We'll start with attenuation, which means the weakening of the strength of the ultrasound as it travels through the tissues, because it's a major limitation of ultrasound. It basically dictates what frequencies we can use and therefore what resolution we can achieve. So the term attenuation refers to the progressive loss of energy as the ultrasound travels through the tissues. There are several causes of attenuation, but the most important usually is the absorption of some of the ultrasound energy by the tissue. So as the ultrasound wave is traveling, some of its energy is taken from it and it remains in the tissues in the form of heat. This, of course, causes heating of the tissues, which will be one of the things we'll look at when we talk about the safety of ultrasound later. Why does the wave lose energy in this way? The reason is that the tissues move in response to the varying pressures. As you can imagine, as the tissues are compressed and expanded and compressed again, there is a small amount of movement and there is friction associated with that. Tissue is not a perfectly elastic medium. There is some friction, and this means some energy is lost in the form of heat. Now, some of the other things that can cause attenuation of the ultrasound are the reflection and scattering of the ultrasound as it travels through the tissues. We'll be looking at these shortly, since they're the mechanisms that produce the echoes which the machine uses to create the image. So some energy is reflected and scattered as the beam is traveling, and of course that energy is then lost from the beam, and so the beam becomes weaker. Most of the time, it's a very small fraction of the energy that is reflected and scattered, and therefore this is a relatively insignificant factor. But some tissues have strong reflection coefficients, and we'll talk about this shortly as well, and in that case, the beam is significantly reduced due to that reflection process. One other mechanism that's less obvious is that there are some situations where the ultrasound beam becomes defocused. Now, I haven't referred to the beam until now, but the ultrasound is transmitted in a focused beam. The machine focuses as best it can because this will produce the best quality image. So sometimes the beam is defocused as it passes through the tissues, and this means that the beam spreads out, and therefore the same amount of energy is spread over a wider area, which reduces the intensity of the beam. So defocusing in some specific circumstances can cause a reduction in the beam intensity and therefore attenuation of the ultrasound. As I mentioned, attenuation is an important limitation of ultrasound. So let's define our terms. If you imagine ultrasound traveling through a block of tissue, as I've drawn here, let's say the initial intensity of the beam is I1, and after it's traveled through a distance L, the beam has been reduced in intensity to a new value I2. So that's a smaller value than the initial one. So we can quantify the intensity by simply taking the ratio of the original intensity to the final intensity. For example, if that number was 100, that would tell us that the attenuation in traveling through that amount of tissue is a factor of 100. However, it's far more common that the attenuation is expressed in decibels. Decibels, as you probably know, are logarithmic units, and there are various reasons for doing this that we don't really need to go into at this point. So to calculate the attenuation in decibels, we would take that ratio of the initial to the final intensity, take the logarithm of that, and multiply by 10. We would then have a number, and that would be the number of decibels of attenuation. Now let's look at how you would estimate the amount of attenuation in a specific clinical situation. If I said, I'm going to be passing 5 megahertz ultrasound through liver tissue which has this attenuation property, what will the attenuation be? So this is the equation you would use in that situation. So you can see that the attenuation, again expressed in decibels, is the product of three different things. The first of these, alpha, is the tissue attenuation coefficient. So that's a property of the tissue. It's going to vary from one tissue to another. A typical average value for that in soft tissue is around 0.5 decibels per megahertz per centimeter. L is the distance traveled, and F is the ultrasound frequency. So you can see it's quite a simple equation, and if we weren't using decibels, it would be a far more complex equation. Let's look at an example so that you can get an idea of the scale of the attenuation. As I said, a typical average value for the attenuation coefficient is 0.5 decibels per centimeter per megahertz. Let's suppose we're using 10 megahertz and we are scanning to a depth of 6 centimeters. So we're looking at tissues that are 6 centimeters into the body down from the skin surface. Then, using the formula from the previous slide, we would calculate the attenuation is alpha times distance times frequency, and that gives us 30 decibels. Now, going back to the mathematical definition of decibels, I can work out from that therefore the intensity ratio must be 1000. So the intensity at 6 centimeters depth is 1,000th the intensity that was transmitted into the tissues. So you can see that the transmitted pulse can be attenuated by an amount of 1,000 times in traveling through 6 centimeters of tissue. Now imagine that an echo is produced at that depth. That's some tissues at 6 centimeters of depth. The echoes produced by that are going to travel back to the probe through 6 centimeters of tissue. So those echoes will also be attenuated by the same amount, by 30 decibels or a factor of 1,000. So we talk about the round trip attenuation. The attenuation going from the probe to the depth, so that's the attenuation of the transmit pulse, and then the attenuation of the echo traveling from the point where the echo is generated back to the probe. And in this case, in this example, the round trip attenuation is 60 decibels. Once again, I can go back and look at what the ratio of the intensity values must be, and I find it is now 1 million. So the echo intensity has been reduced by an amount of 1 million as a consequence of attenuation in soft tissue. So you can see it's a very dramatic effect, a very important effect. Now, coming back to the previous equation, you'll notice that the attenuation in decibels is proportional to the frequency in megahertz. So if I'm worried about attenuation, if I have too much attenuation, I'm going to have to reduce the frequency because then the attenuation will be less. And so that's basically the way in which we can deal with attenuation. We choose a frequency which is going to penetrate to the depth that we're interested in. So let's look at this a little more. For any one operating frequency, there will be some depth at which the attenuation is so much that the returning echoes are going to be too weak for the machine to detect them. And we call that then the penetration, or the penetration depth. And I'm going to represent it with the letter P. So for echoes at this particular depth, there's so much attenuation that we're right on the edge of the echoes being undetectable. At greater depths, the attenuation will be too much and the echoes will not be detected. For smaller depths, the echoes will be detected and will be displayed in the image. So it's the limit of penetration. It's the maximum penetration that we can image. Now, if I calculate the round trip attenuation for this particular depth, it is simply alpha times 2p times f, the frequency. And what we're saying is that that must be equal to the maximum amount of attenuation the machine can tolerate, and I've just used m as a symbol for that. And so we have the equation I'm showing here, that the attenuation coefficient of the tissues times twice the penetration depth times frequency must be equal to this maximum amount of attenuation the machine can tolerate. Now that M is going to be essentially a fixed amount. And in any one clinical situation, the attenuation coefficient is a given as well. It's fixed. And so I can rearrange the equation to show that the product of penetration depth and frequency is equal to the maximum attenuation that the machine can tolerate divided by 2 times the attenuation coefficient. Now those quantities on the right-hand side are fixed for a given situation. And so that tells us that for this particular machine, the attenuation, the product of penetration depth and frequency must be a constant. So now we know how penetration depth varies with frequency. It simply varies inversely with frequency. So if I was to double the frequency, I would halve the penetration depth. If I reduced the frequency to 1/3 of its previous value, I would treble the penetration depth. So there's a very, very simple relationship. In summary then, I've defined what we mean by attenuation and explained the mechanisms that cause it. I've explained that in particular, absorption of energy in ultrasound is the normal mechanism by which the ultrasound is attenuated, and I've shown you that the attenuation is very, very significant. We've then seen that the attenuation expressed in decibels is proportional to the distance travelled multiplied by frequency, and that then allowed us to calculate that the depth of penetration multiplied by the frequency must be a constant for a given machine. Now, it may vary a little bit from one machine to another, but it's going to be fairly similar. So we now have a handle on the way in which penetration is limited by frequency, and you've seen that frequency is the main lever that we have to control the depth of penetration. And in particular, if we need to scan deep, for example, if we're looking at obstetrics, deep abdominal scanning, echocardiography, we need to penetrate many centimeters of tissue. We'll find that we're forced to use relatively low frequencies of perhaps 3 or 4 megahertz. When we're looking very superficially and only penetrating a short distance, we can use much higher frequencies, perhaps 15 or 20 megahertz if we're looking at the thyroid, for example, and get much, much higher resolution. There are even specialized areas such as ophthalmology where the attenuation is very small and very high frequencies can be used. So the resolution then is extremely good. Whereas in the abdomen, coming back to that area, we're forced to use relatively low frequencies and therefore we get inferior resolution. So the resolution is intimately connected with the depth that we're imaging at. The more superficial, the better the resolution can be.